Welcome back. This is another concept problem. In today's video, we want to find the power loss within the battery and the terminal voltage on a load of 2 ohms. So we're giving that with a internal resistance of 0.5 ohms. The battery has a open circuit voltage of 20 volts. And then we're asked to determine the loss within the battery, power loss, and the voltage across the 2 ohms load. So the open circuit, we're talking about this circuit here. The open circuit is the terminal voltage of the battery. So we're going to have 20 volts across here. No current flows, 0 amps. So therefore we don't get any voltage drop across this resistor. So we see the 20 volts of the battery across the open circuit. This voltage will be different, however, when we connect a load across the battery, because there will be current. So in this circuit we have current, so current is I. And then we're going to have a voltage drop, so this is minus to plus. We're just going to call it plus to minus. Plus to minus. There will be VRL, which is the voltage drop across the load resistance. And the voltage for the open circuit is the terminal voltage of the battery. However, when we connect a load resistor, there will be a voltage drop across the internal resistance. So therefore, the voltage across the load will be less than the terminal voltage of the battery. So to find the power loss and the terminal voltage on the load, we need to find the current when the load is connected. So we can find the current when the load is connected as I, and that is equal to the terminal voltage of the battery, which is 20 volts, Vt, divided by the total resistance seen by the voltage source, and that will be Ri plus RL. And now that we have I, we can find the terminal voltage at the load. So we can find the voltage drop across the load and the power loss within the battery. We can use voltage division or loop method to find the voltage across the load. So just let's do both. So we're gonna do a loop. So let's do the loop first. So going around the loop, we encounter the negative terminal of the battery. So we're gonna have negative Vt. And then we encounter the positive terminal of Ri and the positive terminal of RL while going this way. So then we have I times Ri plus I times RL, which is equal to 0. We can move these two over to the right hand side. So therefore we get RL is equal to Vt minus I times Ri. We know this is the voltage across the load, so we can call that VRL. That is equal to the terminal voltage minus the voltage drop across Ri, which is the current through Ri times the resistance of Ri. So we know that the current is equal to the terminal voltage divided by the sum of Ri and RL. And we're going to multiply that times Ri. So therefore we get Vt times Ri all over the sum of Ri and RL. We then go ahead and state that this is the, well, not state, this is the voltage across Ri, and Vt is 20 volts. You plug in the terminal voltage, the internal resistance, and the load resistance. That equals 4. And we see that the voltage across RL is equal to 16 volts. we can just go ahead and simply use our voltage divider equation, which you'll see that in the loop method, we had stumbled upon that as well. So that is the voltage, and we're doing the voltage divider equation. The voltage across RL, which is our targeted resistance, our targeted resistor, is equal to the terminal voltage, the voltage of the voltage source, times the targeted resistor, which is RL, divided by the sum of the resistance seen by the voltage source, which we'll see a replica of this one. However, though, the target resistance or the target resistor is the internal resistance, and over here the target resistor is the load resistor. So the target resistor is the resistor that we want to find the voltage drop across. So then again, we see that this guy now evaluates to 16 volts, which is using both methods. So we can finish by finding the power lost in the battery. So with current, so we know current and we know the internal resistance of the battery, so we can calculate the power loss as P is equal to V times I. And we know that I is equal to V times, well, V is equal to I times R. Well, this should be I again. So we see that that's I squared times R. And in this case, we want to know the power lost, or the power for the Ri resistance. So I want to see the power loss of the battery. So power loss, internal resistance. So let's go look to make sure. So yep. So I want to see the power loss within the battery. And within the battery, there's an internal resistance. So we should only consider the internal resistance when we're considering the power loss. So we know that current is equal to the terminal voltage all over Ri plus RL. And that should be squared. So that's Vt over Ri plus RL. That's squared. And that's times Ri. And we see that the power is then 32 watts. And that we'll just call that lost. So we can further explore this problem by finding the total power. So let's just find the total power. So we have the power lost within the battery. So let's find the total power of the battery. So that will be P equal to V times I. And we have I and we have V. So if we evaluating I becomes 8 amperes. So we know the voltage is 20. So 20 times 8, we then get 160 watt. So that's for the battery. We can then, as we just said, calculate the power consumed by the Ri resistor, which is the power lost. So that would be, let's just do it this way. So that would be P is equal to, well, PRI. This is the power loss caused by the internal resistance. And we know that the voltage across the internal resistance. So we're going to use V squared divided by R for this, Ri. And we know that the voltage drop across the internal resistance is 4 volts. So we know that we're going to have 4 squared divided by 0.5 ohms, which we then get is 32 watt. So we can see that both of these matches up. For this one, we use the voltage drop across divided by the total resistance. For this one, we used the current through multiplied by the resistance. However, this current is going to be squared. So then we can go ahead and find the power across the load, or the power consumed by the load. So that would be P, let's write it a little bit larger. it will be PRL is equal to, and I think that was 16 volts. 16 volts for the voltage across the load resistor. So that'd be 16 squared divided by, and I think that was 0.2 ohms or 2 ohms. So that's 2 ohms divided by 2. So we get that is equal to 128 watt. And we can then check the conservation of power. And we know that the sum, so the power of the battery, is equal to the power consumed by RL, or the power converted, consumed, whatever you want to call it, and RI. So that should equal to 160. So 32, well, this should be 128. 128 plus 32, and that is equal to 160 watt. So that's it for today's problem. I'll see you in the next one. And to go over that again, when the circuit is open, that voltage at that open, or the open circuit, will be equal to the voltage of the battery. And once a load is connected, there will be a voltage drop across RI that will affect the voltage seen across the load. In the previous video, we had found, or I think we had, well, not think, but we'd evaluated the power, the maximum power condition, and we expressed that the power delivered to the load, which was when the load resistance is equal to the internal resistance, so that's we match the resistance, we get that power is at its maximum at that condition. And whenever that happens, that would be 4 times RI, and that should be less than V squared divided by 2 times RI. So in this case, if RL is equal to RI, we then see that, if we can find that expression somewhere, well, we can just look at the circuit to find the power. If RI is equal to RL, that would be the total resistance of the circuit would be 2 times RI, or 2 times RL, wherever you take it. And then we could just say V squared divided by 2 times RI, or RL, would give the power. And however, though, the power delivered to the load cannot exceed this guy. I'll give a link in the top right. Go and watch that one, and you'll get a more intuitive understanding on what I just explained. So I'll see you in the next one. Bye.